So welcome everyone for cloud computing and big data. Today we have our lecture 6 on deep learning driven by big data. So that is a very interesting topic. It will now build on elements we have learned on lecture 2, basically with respect to the Perceptron learning model. It was one of the simplest learning models that are existing, yet it is actually one of the building blocks with basically being a neuron in the big neural networks that then lead us to the deep learning networks. So it will be a very dense lecture today, and this would be something where at least you take away this to many different application domains, hopefully, and maybe inspire also here some interest for those that really want to engage in this topic. We have also a deep learning course at the university. Is someone taking this by chance? Was Magnus or has taken it? Deep learning? Not yet? Okay. So if you find this interesting, this topic interesting, then I would encourage you to take it. We will have around 3 lectures on this topic just because it actually is harnessed and really nurtured by big data. It leverages cloud computing and HPC a lot, and that's why deep learning is a relevant application field for us here in the cloud computing and big data course. But let us connect a little bit what we have learned the last time, which was then a practical lecture 5.1. Which I had basically pre-recorded. I couldn't be here in class, sorry for that. But there we basically have shown a little bit what the MapReduce approach entails, how it is really implemented. Just as a reminder, again, it could be very relevant for your exam. MapReduce is not just MapReduce, it's map, sort, shuffle, group, and then reduce, right? That's a very important takeaway message. The keys, the shuffling and sorting around, that is a key paradigm idea. And then the other part of the paradigm is really this embarrassingly parallel idea, nicely parallel as we call it. So it will not communicate a lot with each other. Right here we're talking about lots of map tasks, then there's one big shuffling, sorting, grouping, and then again lots of reduce tasks, and then the outcome. Divide and conquer, right? So as we learned. So this is something where this is a principle in computer science implemented here basically with MapReduce in the Hadoop framework, also in Spark, I should mention. And the way the practical lecture was alluding to, we firstly, of course, showed it a little bit that in HD Insight, this is possible as well. Obviously, they have the same stack in HD Insight as the Google Cloud and the Google Proc services or the Amazon Elastic MapReduce. Now, when you think about this high-level picture I presented to you many times in the beginning of the course, where we said, well, the cloud is this magic thing. That's why we call it cloud. It's elastic up and down in terms of EC2s, this elastic computing services. We have basically gotten to a more concrete idea of what we really need to create an elastic MapReduce cluster. And the first takeaway message was really, we need more than just compute, right? First, we need some security. If you remember, we had actually created SSH keys, which are fundamental in administration. It's probably your daily business, right? SSH keys in a way. So something where, cluster administration, when you want to have the cluster remote access, usually you always need SSH keys. And internally, to make the management of the cluster working, it also is relying a lot on these keys. But the second point was also that we basically have to store results of computing somewhere. Hence, we have learned about the S3 service from Amazon, which was basically the storage alongside it, right? So this is the first things we do. And if you remember in the demo that I gave in 5.1, I created this class demo. We didn't came in the lecture in the end to it because the MapReduce was not finished, but you see here on October 4th, at some point in time, it was really a success. And then we had the different parts from this different reduce task that you then, of course, have now to combine for an output together. And if you look inside this, obviously no basically big questions, but the word counts are in. So in a way, we have configured security in step 1. We have basically put some output directory where basically the word counts can be dropped. In the second step, now obviously we had to create the cluster, which then, if you remember, was connecting to this SSH keys. We had to put them in. And then we had to define, of course, how many compute resources we would have, right? And there was, again, the usual suspects in terms of table, more memory, more costs, GPUs, more costs. The same thing we have learned basically in MS Azure, if you remember, right? With the tables, with the money you have to spend. The same is also in Amazon. And you can go on, all cloud vendors have that today. because that's how you steer your spending. And of course, the performance of the cluster, especially in Spark, as we learned, in memory is incredibly important. Then basically here you go away and take, the price for it. You see here a little bit, hopefully it's not too small, the charges that we have got basically for this simple cluster, which was just a couple of, little compute items. And here we're really talking about a teaching cluster, which has, let's say, a couple of nodes. And if you now go to production in a company with 100 nodes, you can clearly estimate now, maybe by factor of 5 or something, what terms of cost is this, just for a couple of days, right? Since I basically gave the demo, this thing is running again. And since then we spent $36, which is not much, but think about that we didn't use 100 worker nodes, we used just 2. So in this sense, something where you have to steer, of course, and think at the company. And the more important thing, that's why I do an exclamation mark, terminate the clusters. Right? When you're in the company responsible, you go on vacation for 4 weeks, the cluster is running, nobody's using it, you have to pay, right? It's pay per use, but the cluster resources are used with your elastic MapReduce, the same as in HD Insight. Even nobody uses this, as the name suggests, pay per use, but no, you already have configured and deployed the cluster EMR on it, so there you go and have to pay the price. And this is something which many people underestimate or basically forget or so on. Now, luckily, we have seen there was an auto termination feature that was quite valuable. And of course, something you should leverage when you go to the company, because your bosses will be very angry if you spend suddenly 10,000 euro in cloud resources, which was not expected, but just 1,000, right? So here in the teaching domain, we keep it to a reasonable few, but in a real big company, this can quickly become an issue. Right, and in the force, we of course run the word count example in MapReduce, admittedly a very simple example, but it captures nicely the essence of the key value pairs that you have. And of course, if you remember, the power now of Hadoop would be really thinking about combining it with HBase, combining it with Mahout, machine learning implementations for map and reduce tasks already. This large ecosystem that we basically see here. You see a bit here, HD Insight, Hive, for instance, for SQL, as we already used in the course, and so on. So this is a large ecosystem, and these services, as we have seen now, are available in HD Insight, in Amazon EMR, and needless to say, the Google Cloud has a similar idea of the Google Proc services. But let us come a little bit now to the topic of today. You see it's also a practical topic, so I will do basically a simple conceptual start again from Perceptron, bringing you to neural networks, and from neural networks to deep learning. Obviously, when I was saying there's a whole course on deep learning, I cannot go into details in all of this significant way, but here we capture the essence of some of these topics that are relevant then for your assignment 2, which I will hand out actually next week. So with this, basically, we will have the conceptual basis to understand deep learning and its relationship, why it's computationally expensive. And then in lecture 7, we will complement this with some applications in clouds. And then one of my PhD students will give you basically an invited lecture on distributed deep learning that then really captures the essence why cloud resources are really needed for deep learning. Otherwise, you do it in a very naive way. So fasten your seatbelt for a very tough lecture from one perspective. So conceptually, it's a little bit math here and there, but I keep the math to a reasonable degree, as I was also alluding to in the beginning. We will connect with what we learned already in lecture 2. So everybody that has not done deep learning before, don't worry, we will do it stepwise and go to it. But as I said, also, if you like this topic, you better be also visiting the machine learning course, or the deep learning course even from Magnus is also probably a good connection to this. Here in the course, we put an emphasis on what is now the computational intensive part and the big data part of it. So as I said, we start a little bit with the linear learning model again, the idea of what is a neuron. We connect with our old example, the MNIST that you already know, the handwritten character recognition. And then we actually extend this to something we called multi-class classification. So we stop with this binary. As we were already known, this MNIST is basically 10 characters. So we have multi-class classification. And we'll grow the perceptron to something called multi-output-perceptron with this. And then basically go to fully fledged artificial neural networks, which are sometimes also called multi-layer perceptrons. What is important for us to recognize in the cloud course is we have more trainable parameters out of that. And I will give a point at each of the conclusions of these different models. And here and there, I give you some machine learning on the way. Things like overfitting, underfitting is a very important concept that you have to understand, because there are really difficulties and problems when you come to real life applications. However, the course cannot teach you a lot in regularization and validation, which are both actually the cure for overfitting. So in this sense, just take it, as advice. Then in the second part, we have let the base with artificial neural networks on a quite fast pace, I agree. But still, you have the base for moving one step ahead to deep learning. So what is now the idea of deep learning? Some of you already know. It's not just doing more and more neurons deeper and deeper, right? There's a smart idea to every of the deep learning models you have, and I will make a point on it. Still, we're talking about shallow learning when you have maybe typical artificial neural networks in terms of 2 layers. That's called a very shallow network. And my PhD students use something like ResNet 50 and so on, with more than 50 layers and even in the hundreds right now. And I give some examples, but also Rocco, who will give the invited lecture, will give you a very nice overview on this in the particular field of remote sensing. However, we concentrate here on the MNIST dataset to connect what we can do better from the neural network. There's something like spatial aspects we can consider, where convolutional neural networks, for instance, have a very good role to play. With this, we have a little bit the CNN architecture, although we have to connect in this again on lecture 7 and again with Rocco also in practical lecture 7.1, right? So everything today will be here and there still some question marks in your eyes, but of course we will dive deeper here and there in the next couple of lectures. Another point also to understand is really then the complexity of all the hyperparameters, the trainable parameter, which then really make the big case for cloud computing and HPC. Right, again, to repeat, basically today, if you want to have really good accuracy, cutting edge models, you cannot do deep learning without HPC or cloud resources. That's basically impossible. Even if you leave your laptop, let's say, running for 5 days on the big deep learning networks, you have to do the hyperparameter tuning to get the accurate hyperparameter. And this means you have to do this maybe 100 times, and then your laptop would be all the year running. But this is something we will build on the next couple of lectures. Of course, for toy problems, you can do deep learning and it will work in 1 hour on the laptop. As you know, the MNIST example, for instance, is a toy problem. This is handwritten character recognition. This is a different aspect that we have in applications, and that's also something I would like to give you on the way. Some applications where really this is cutting edge in terms of where you use deep learning. But yeah, let's come to the first basics. And maybe my first question is, who has used deep learning maybe before? Someone? Artificial neural networks, like 2-layer networks, shallow networks, a little bit. Okay, good. Then it's good that we have basically an introductory part here. So we assume nothing, only our lecture 2 materials, right? And that's the now basically introduction. If you remember in the lecture 2, we had a little bit about the perceptron learning model, this linear learning model. You remember jumping around heavily to do binary classification, 0, 1. Or +1, -1, depends how you model it. A key essence was in that part that it was a supervised scenario. In other words, we have the input vector with all the features, but we have always this guiding y, so we know which class it is, right? So in a binary classification problem, n is here basically just 2, so we basically have just 2 different classes, but today we will extend it to 10, for instance, for this handwritten character recognition. But supervised learning is by far the best understood one these days, although really successful models like transformer models we use in research right now are really cutting edge and not really supervised. So also there are good models in the, let's say, not supervised learning area, but at least supervised learning has shown and basically is the modus operandi of many of the learning tasks today, because it's the best understood one. To connect then a little bit what we had done in lecture 2, we had the idea of basically creating a machine learning model that can distinguish between the 2 flowers, if you remember. And we came up to the brilliant idea that basically we have a line in space, which makes it a linear perceptron model. We learned it over time, and then basically could resist saying everything above that would be, let's say, the iris virginica, and everything below this interesting decision boundary would be then the iris setosa. So this was a simplified scenario. There was not a class overlapping. In practice, we have that, unfortunately. So what I sampled out for you was a class that actually is overlapping here a little bit with the features. and then the perceptron would not work anymore because it would be not linear, right? Because it would be very wiggly curve to basically get this through. And even that is not what we want in machine learning. So I come to that step by step. So what we basically can generalize out of that to go towards neural networks, to go towards deep learning models is essentially this slide. It connects a little bit what we had basically the last time, if you remember, summing up the weights using basically then the weights that we learn. So sum them up linearly. We had this interesting bias that you need for a line. If you remember, we incorporated this for mathematical convenience because in the end, the W0 we can also learn, right? We just put there's another trainable parameter. What we not really thought of was this fellow, a G, which was a nonlinear activation function. There we had just a simple function saying +1, -1 step function. Today we will learn putting there a non-linearity function will provide us many benefits. And this is something what we want basically to achieve. So just for you also to think about what we have already as constants here, right? That's our data sets. So we have always a different axis. This is given to us. But what we want to achieve is to have these weights learned. And that's something what we want to do essentially with machine learning. And I already was basically showing you a little bit when we did some data exploration, this MNIST data set, when we did the basically idea about Python and looking into this. So there are 10 classes existing in this data set, and we have looked at the digits a little bit by looking, and using some smart Python code. You have seen basically we have a 2D problem. And this is very important to understand. It's a 2D problem with a guiding label, right? With grayscale numbers, which then basically incorporate what digit we see here on this image, which is, of course, in the end, just numbers again, which we know from computer science. So also what we learned a little bit already was training set and test set. That's also what you should always do, cut them away in different sets. And if you swim in data, you maybe even do 3 validation sets, throw them in the corner. But this is something which is more for a more advanced machine learning course, and we come to this maybe a little bit in the next lecture. Then the tools that we use also for neural networks would be basically TensorFlow and Keras here in the course, but many of my PhDs use, for instance, PyTorch as well. Some have started to play a bit with DeepSpeed as well. So basically, however, I think PyTorch and TensorFlow are the most known artificial neural networks, and then also deep learning packages I would recommend. Keras is particularly good for teaching because basically it encapsulates the layer structure better than basically TensorFlow itself or PyTorch. Hence, these examples are basically done via Keras, which is now part of TensorFlow distribution. And for us in the cloud course, very important is that they leverage GPUs significantly well, and also CPUs if needed. And one part of your assignment is to find out why GPUs are so brilliant for deep learning and neural networks. And this is also something we have more in lecture 7 when we come back to these. Once you have built the fundamentals, what are actually neural networks, before we talk about how basically they benefit from GPUs especially. Yeah, for playing around with this, the Google Collaboratory cloud infrastructure is there that is used for you if you want. It's already there for everyone for free. If you have the pro version, you can pay something around $10 and get a bit better GPUs. And there you can already get the differences. Just for some of you that want to play around with this. Still, I want to show you there the limits that basically we have just one TPU or GPU available. Sorry, I got a bit cold, I think, So, and we want to advance with this, right? So if you're using the Google Collaboratory, it will not help you with cutting edge deep learning, right? So if you have cutting edge deep learning, you need more and more and more GPUs. The Google Collaboratory gives you just one. And even this one will basically differentiate between Kepler architectures. Sometimes you're happy and get an Ampere. So you even not have the fixed amount or the fixed version of a GPU available, you're jumping heavily. Hence, what could help going to the cloud. So there you would have Amazon Machine Images. That's something we will explore more in the course, where basically I was alluding to with virtualization already, that all the pre-installed setups are already available, right? Which makes it very powerful. In the AMI, which is essentially just a virtual machine image, is everything encapsulated in all the different things we need, TensorFlow installations, PyTorch, things from the lower level libraries we need for deep learning. Here, for instance, you see Nickel or cuDNN, which are good for NVIDIA GPUs. So this means we have all of this installation nightmare not to do, right? All the packages should fit to another, and basically then, needs to be executed on the cluster. And the beauty is here, of course, as you know, we can scale. The Google Collaboratory is fixed on 1. So that's it. If you want to have ResNet 50, good luck. Basically, if you want to go better in machine learning and deep learning, go to the AMI images. So this is perfectly supported in Amazon. And of course, no surprise, all the other cloud vendors do the similar thing. It's not called AMI. That's just an example here for you. Now, when we look in the data set again to understand neural networks step by step, we had already this data exploration script in one of the earlier lectures when we learned a bit about Python. So there's a small kind of, let's say, code that you have here where you have the training and test set. And the beauty is in the MNIST load data, this is already let's say, package data set of. So you can easily download this and play around with this. We had created a small, let's say, function for characters to show each of the characters to understand now this two-dimensional problem. This two-dimensional problem will be a challenge for neural networks, and I will make a point on it. So that's why it's important for you to understand data exploration is so important, because you have to understand certain things. We go here just to do the first couple of handwritten characters. You can have 100. It's not so important how many. The important is you grasp the idea that in the end we have a two-dimensional problem with digits, right? Hence, if you put it into one-dimensional, you have to do a vectorization. I'm not sure if you learned this concept, maybe in 101 computer science, vectorization. So putting a 2D in 1D, it's basically a very simple solution. We will talk about it. But it's a very common concept in basically computer science. But what could be the problem if we go from 2D to 1D? Any idea? Yes, exactly. The spatial information, we call that, right? So basically you see here beautifully in one of these, we know exactly my neighbors, right? And this is beautiful. So chances are if I have something like a figure that the next, let's say, pixel maybe has also something on it. So let's say some ink or whatever. And the next and the next. So the neighboring information gets lost if you vectorize. Hence, we will later in deep learning pick that up and keep the spatial information and achieve better results. I give the story in front so that you draw some attention on it. Also, when you do Jupyter, you have to connect to it. When you do the AMI interfaces or other, let's say, cloud vendors, usually they have specific environments. You see here the very specific TensorFlow. For instance, just take away the message that sometimes you have to also in Jupyter with different kernels pick the right version. So talking about this, what I just said, need for reshaping. When we see the perceptron, it was just a 1D input, if you remember, right? It was just one long vector we gave in all the time. And over time, this perceptron did this hopping around, updating, subtracting a vector or addition of a vector. Now we can't do this and give that as an input. We have 2D. So what we have to do is to reshape it, to vectorize it, as we just said, losing information. And this is something which you always have in machine learning. You have to basically balance this. When you want to reshape, is it really good? The same as, of course, if you have high dimensional input data. Today, we talk about the iPhone and so on, such resolution pictures, but you cannot just stick that into a deep learning network. It will be far too computation complex. So you crop it or you reshape it, losing information, right? So something to think about when you do practice analysis. And here we basically see that in practice, it's no magic to do this, right? So in the end, what we do is we take every little fellow here on the line and then put it as one long vector. So in the end, there's no big, let's say, rocket science behind it. We normalize it sometimes to do it basically as you see here, so that the numbers are between 0 and 1. So that we not have, let's say, out of bounds and so on when we come to the capacity of integers, for instance, when we multiply a lot. Multiplication was inherent, if you remember how we did this with the perceptron learning model over time, always basically summing up linearly using weights. So by reshaping, we have done the first step. So we have a 1D input, and we can do this now. We can give basically the image into this neural network that we will create now step by step. First, let us start where we begin. That was a perceptron model, but with a binary classification output, 0 and 1, or +1, -1. Hence, we have now to do a multi-output perceptron model that has more outputs, and the outputs would be, of course, our guiding Ys, which is 0 to 9, right? The handwritten characters. And you see how that nicely can be done in Keras, the sequential model in Keras. You would say it's still a dense network, dense in terms of everything is connected with each other. And this is important because we'll talk later in deep learning again about it, that we get rid of some of these properties, not completely, but for some aspects. Then we have a so-called softmax layer, which is a function which presses everything between basically our output probabilities that we have to extend a little bit here for the, let's say, 10 classes that we also give as an input basically to the model. For us, important is here not only this number of classes and the Reshape vector. With this, we have a neural network which has around 8,000, trainable parameters. That's not much. So here you can use your laptop. Just that you basically get a significance of growing now. This basically comes from the parameters you have times 10 classes, right? We do this with 10 neurons here. And basically you have 784, which came from the vector, right? This 2D problem put in a vector, meaning we have 784 pixels as input. And by doing this, plus the bias that we learned, we basically end around 8,000. So the exact number is not a really important part here because we will grow significantly, especially in deep learning. So with doing so, this is something where now the computing is happening, basically learning these parameters again and again with the optimizer function. We learned about SGD before. I told about you the error function, then going downhill, the error. I think we have basically talked about this already, and machine learning courses will go there in much more detail. But for the basically multi-class also, we go for the categorical cross entropy here. It's just better for this particular given problem at hand. And when we do this, we can easily compute this by using basically a little bit of Keras here from the idea of using the optimizer SGD. It's implemented. We can define the number of classes, batch size, and epochs is how often is a data set basically iterated. And this will be one of the hyperparameters you have to steer later, right? So there's no given certainty that the number of epochs 20 is enough. Could be 30, maybe 10 is enough. So this is a parameter that you pick out of your heart, so to speak, or some application experience, but there's no certainty. So you have to experiment around that. Here's then the reshaping taking place that we discussed, the normalization, basically to have the values between 0 and 1 for mathematical convenience. And if you print them out, of course, you see the training and test parts. The beautiful thing here basically in Keras is that you can create these layers now sequentially. As we learned, the dense model was basically good for us, but here we talk still about a perceptron, not a neural network. One multi-output perceptron, hence there's basically still one layer only. The input, of course, is one of it, but then also the neurons in the perceptron layer. We say we want to have an activation function after it, which is a softmax for getting probability. So we will get not an exact saying it's a 7, it's an 8. There's a probability of having a 7, a probability of having an 8. Why? You see also when you compare 0 and 8, for instance, in the output, it has quite some overlaps. So it could be 0 or an 8 with some probabilities. And then you have the optimizer, which is then basically our SGD. The metric that we want to have is an accuracy to saying later on what exactly we are after. And of course, the kind of loss function that we want to then optimize on, right? This is then where this downhill is taking place. In the fit function is now where the computing really starts. As you already know from the logistic regression, now we're one step basically more in the output perceptron model, and it will compute a lot. And that's where the computing comes in, solving this 8,000 parameter problem, right? So we determine the weights of 8,000, which is not much, admittedly. And of course, in your assignment 2, the idea is to experiment with this, to really play around with this a little bit so that you get a feeling for it when you do it yourself. So running now basically the neural network with no hidden layers was the idea. That's an important part, multi-output perceptrons. You see, we get an accuracy of 9.2. right? And this could be now something where you have lots of optimization to do. One of the things could be you do 200 epochs. You remember we had 20? Now I do 200 epochs, so I learn these samples again and again and again and again. And usually a machine learner would say, careful, because when you learn too much, you basically do something called overfitting, right? So you start learning each sample by heart if you do too long learning. Hence, we need something like regularization, which a machine learning course is probably like 3-4 lectures on, to really regularize this so that you come to a more smoother curve, because it doesn't make sense to learn each sample by heart. It is very prone to overfitting, and then basically the neighboring point, which is very close here, will be wrongly classified. So still you see this 92% accuracy here from this run. And as I said, it will be also part of your assignment, so you will do it yourself and it becomes more into mind. But you see we're ending up with 9.2, we cannot improve to 100 apparently, or not better. So what could be solutions here now when we think we have one neuron? We combine different neurons. And this is the beauty of basically the idea of neural networks. So we want to beat essentially this 9.1 basically percentage or 9.2. There's sometimes some basically, stabilities, which could be always, it's not directly the same value, but it's around 9.2 or 9.1%. Hence, we can do more hidden layers, more neurons in the hidden layers. So now we can do the magic of neural networks, basically. And that's what we're going to do stepwise now. Because essentially, if you think about what we have done so far from a neural network perspective, we have just one neuron. The perceptron is modeling a neuron. I have a video that is also summarizing this later. But with this linear learning model, there are lots of non-linearities that you can't catch. And one example is here the XOR limit that some of you know from basic computer science. There is not a straight line where you can separate both of these points, right? XOR is well known for basically this paradigm that you have here in the table, or the colors that you see here, while maybe others can be learned, this XOR is impossible with a linear learning model. Hence, what the idea of artificial neural networks is, or multi-layer perceptrons, combining them in different layers. So we introduce a hidden layer. Still, we need the input layer of the basically inputs that we get from the image, but we combine in the hidden layer more perceptrons. And how many is now in hyperparameter. Can be 20, can be 200. But of course, for each you do, we have a different weight connection. And this weight connection needs to be learned. Hence, more computing needs to take place. But by combining, for instance, what you see here, just 2 perceptron in the hidden layer, you catch this non-linearity with the XOR by basically having these 2 lines learned. So this is still just the beginning, because we will learn also there are lots of non-linearly activation function. But to go into all of these details, there you really need a machine learning course. Take away the message that you introduce this essentially as one of your choices when you create basically the neural networks, and you then can basically put that in front each of these different neurons that we have seen already. But now we have, of course, much more neurons going through all of that, because we have all of them dense connected. So hence the idea why we do this is essentially, you see a sample here. If you have a nonlinear data distribution here, as we had with our perceptron learning model, linearity can never learn that. But the combination of many nonlinearities can actually come then to an error, basically, that is almost maybe, let's say, a couple of points would be misclassified, but still a very good accuracy of these models. And for this, the nonlinearities are essential, because as you see here, it's not linearly separable data, right? What I told you with the flowers, right? This was a linearly separable problem. Here you see a non-linearly separable problem, and this will be by far the most in practice. So hence the flowers are another example of a toy problem, so to speak. So knowing artificial neural networks now, we can combine them. There would be a backpropagation of error algorithm, how that is working on a chain rule. It would take at least one complete university lecture to go into the details of the chain rule or backpropagation. I think the machine learning course will probably address that. For us, is we're taking this algorithm basically for granted and say basically what helps us is that we know already the guiding output Y, right? That's our data set. We know from all the digits that we have, it is a 0 or 7 from our training set. So we can have the error computed. Is it really a 7? No, it's an 8. So we compute the error back with backpropagation. That was the breakthrough actually of neural networks in the 70s, so that they invented this chain rule and backpropagation mechanism. Very important for practice in machine learning. And by doing so, we apply essentially the same idea of the weight updates that we already know, but now, of course, on a much more higher scale, we have much more neurons. And here you have different elements how you basically can steer that. There's a so-called learning rate, which is another hyperparameter, right? So this determines how quickly you go downhill the error surface, right? This is an example where we go step by step, maybe too small learning rate. That means we do computing again and again and again, and we do just little improvements in the accuracy. On the other end of the scale, if you're overdoing it with a large error rate, you see essentially we ping back and forth the error surface, right, until we come to the best solution, which could be the local or hopefully the global minimum. But this is something where basically determine the learning rate is one hyperparameters, where we will connect in lecture 7. This is where cloud computing also can help tremendously. And not only with the computing of the gradients, also determine the best learning rates, for instance. And with this, you basically go down the error surface to find, hopefully then basically the trained set of weights with all of these updates, step by step, in each of the iteration of the epochs that we have seen. 200 epochs, long time, lots of compute. Hence, we need computing like clouds and high performance computing for it to do it really at scale. Then when we see how we implement this, it's just a short addition, things you already know from the other model. Here we now just changing a little bit the setup of the different layers. Instead of having a multi-output-perceptron, we introduce this idea of 2 hidden layers here, where we do a non-linearity called rectified linear unit, a ReLU, that essentially then will basically give us here the non-linearity in each of the different neurons before when you compute the input. Everything is still dense connected. There's a weight to every other neuron in the next succeeding layer, right? And this is, of course, high amount of parameters to learn, because all of these weights is something we want to learn, as you know from the beginning. And what we can achieve with this is 97%. So we improved. We're catching non-linearities in the data, and we have now basically a very powerful model. And if you evaluate, just to do a yardstick before we enter deep learning in the second course hours, we have this 91 with 20 epochs in multi-output perceptron, ANN with 2 hidden layers. We have after 20 epochs 95. You maybe can improve a bit if you do 200 epochs, but there you go with the computing price, because you see suddenly from 8,000 parameters, we basically now have 118,000 parameters. And these are all computing intensive, all need to learn, right? Hence, we need more and more GPU power to really get that going quickly. And that is basically the idea I wanted to leave you in the first part of the course hour. I have a very nice short summary of that in my mind that hopefully helps you a little bit again to capture the essence of that, what I just told you before we go to deep learning.
This is a simulation of a single biological neuron. Information flows in, is processed by the neuron, and the results flow out. This gives the neuron its abilities to react based on previously learned patterns. Technology duplicates this by creating a structure that processes information like a biological neuron does, except this process is mathematical instead. Just like the biological neuron, information flows in, is processed by the artificial neuron, and the results flow out. This single process becomes a mathematical formula that can be used for simple problems. For those that are mathematically inclined, this will look similar to a polynomial. A polynomial is limited to the problems it can solve for, as shown in this graph of an order 5 polynomial. If this is all artificial intelligence could do, it wouldn't be much use. As with the brain, artificial neural networks' power is in connecting sets of neurons together in layers. When you connect them in layers, the mathematical formula becomes something like a multi-dimensional polynomial. This allows complex problems, like what is shown in this graph, to be discovered and used for our benefit. As before, information flows in and results flow out. but this time the input to the second layer is from the output of the first layer. The exact steps for a single layer are simply repeated for each layer of the neural network.
All right, so break here for 10 minutes and then we learn a bit about deep learning. Yeah, 1 second. I just finish the recording here. Up.